So up to this point, we've been looking at regression problems where the target that we're trying to predict from our input x is some scalar real number, something like house prices. We're now going to turn to classification. In this case, our output y is a label, a class from a finite set of categories that we want to predict from our input x. A simple example would be something like spam detection, where our input is an email and our output y is a label saying whether this email contains spam or not, a yes or no type of label that we want to assign to that email. In this video, I'll also give some other examples of classification problems, and we're basically just going to look how we can formalize this task of classification. So just to put that a little bit more formally, in regression, what we were trying to do is we had some input, maybe a feature vector x, from which we tried to predict some scalar output y that could be any real number. In the case of classification, this is different. We're given an input feature vector x, and we're trying to predict a categorical class label y from a finite set of classes. So some examples of this would include something like disease diagnosis, where the aim is to predict whether a patient is healthy or not, whether they're suffering from some disease or not. Another example would be text classification, where we try and classify a document, a text document, according to some topic. So you might get in, for instance, a news report, and you would want to classify whether this is political news, whether it's sport news, whether it's news about the weather, and so forth. A third example is maybe something like fault diagnosis. So imagine you've got some engineering system, maybe a photovoltaic cell system, or even something like antenna, and you want to predict from the current operating measurements whether that system is operating as expected or not, whether there's a fault in your system or not. So let's formalize this a little bit, and we'll specifically look at the target output at y. How do you encode the different classes numerically? In regression, this is kind of easy because y is just some real number, so it's already a numeric representation. But for classification, we need to basically make a decision of how we're going to encode the output y. As in a regression, we're going to be given a set of input-output measurements, and the label y should tell us which class the input x belongs to. So if this is my nth data point, and then this should be the input, and yn should tell us what class that input belongs to. There's actually a number of ways to encode y numerically, and I'll just talk about a few here, and in some of the later videos where we look at pre and post processing, we will have a closer look at other ways to encode y. If we're doing a binary classification task, that's something like spam detection, where it's a yes/no answer, then you could encode the output y as just coming from a set which is either 0 or 1. It's spam or it's not spam, for example. Or you could do something like encode y as a -1 for no or false, and a positive 1 for yes or true. If we're in the multi-class setting, that's the setting where we want to predict whether our input corresponds to one of several classes, not just a positive or negative class, but maybe up to k classes. Then one way to encode the output y is to say that it needs to take on one of a finite set of values. This would be class 1, class 2, class 3, and so forth, up to class capital K. So when we're trying to classify, for instance, text documents that might come from the news domain, then class 1 could maybe be sport, class 2 could be political news, class 3 could be weather, and so on. So one dataset that I'll kind of use as a running example while talking about classification is this iris flower dataset. It's a really, really famous dataset. It was something that Ronald Fisher used, and he was both a statistician but also a biologist, so he really liked this dataset. And this dataset basically records different type of irises. And specifically what they did was they measured the different widths and lengths of different irises, and then recorded the width and the length of the different leaves, and then wrote down the type of iris that corresponded to that width and length. So we're going to learn a little bit about irises very quickly. This leaf on the side here, that's called the sepal leaf. This one here. And then this one here, that's called the petal. And I actually have no idea whether I'm pronouncing those names correctly, but that's how I read them. So I might be wrong, and then you should please forgive me. And what they did was they basically measured the petal width and the petal length for different irises, and the same here. Width and the length of the sepal leaves. Okay, so these biologists, they went into a field and they picked irises. And what they did was, for each iris they picked, they noted the petal length and the petal width, and the sepal length and the sepal width. And what they also noted was the type of iris. So apparently you get multiple types of irises, and they wrote down whether this was a setosa iris or a versicolor iris or a virginica iris. And they collected a number of data points, different irises, but all the irises from one of these three classes. And then for each iris that they picked, they wrote down petal width, petal length, sepal width, and the type of iris. Okay, now the question is, if you've got a data set like this and you're like me, I don't know anything about irises, and I now go and walk in the field and I pick a random iris. And I know a little bit about irises. I know about petal leaves, these kind of side leaves, and sepal leaves, these kind of main leaves. So I measure them using a ruler, and then I put it into a model. And what I want that model to kick out is, I want the model to tell me what type of iris this is. Is it a setosa, a versicolor, or a virginica? Now, this data set and this task of iris classification were really made famous by Ronald Fisher, who tried to use this data set as kind of a platform for testing different classification methods. So we can't visualize all the points because they're like in 4 dimensions, but one thing we can do is we can plot just 2 of the features and then visualize that in some way. So here we've got the sepal width on the y-axis and the sepal length on the x-axis, and we've denoted the different type of irises with these blue colors, that's all setosa, the orange circles, they're all versicolor, and then the green diamonds, they're all virginica. And the question is, if I have a data set like this and I go and walk in the field and I maybe pick a flower and it's got a sepal length of, I don't know, 6 and a sepal width of 4, so it's somewhere here, what type of iris is that? Can I build a model that can classify this iris according to one of these 3 classes? And we'll use this data set to look at a number of different classification approaches. It's a nice data set because it's easy to visualize. Sometimes I will note the petal width and the petal length here, and sometimes I will mix the features, and we'll see how different classification models perform on this data set. I should say that this data set, it's very nice because it's so simple, but it is kind of idealized. In a real world example, though these flowers do come from the real world, the data will probably be a lot more noisy. There will be a lot more overlap between the classes, and you will probably have a lot more dimensions. Here in this visualization, we've just got 2 dimensions. The entire data set just has 4 dimensions: sepal width, sepal length, petal width, petal length. And in a real world setting, we'll probably have a lot more dimensions.